All right, so let's talk about 1.7 here, inverse functions. Let's look at the introduction. It says, consider the usual function machine as sketched below. So you've got some function, f, and we're going to shove in an x, and we're going to shove it into this function f, and what we get out is the f of x output. That is, we have our input over here and our output over here. And remember, you can just as easily call this y. All right? The question in this section wants to know what happens if it is asked to operate in reverse, as below. So like this. As in, you take the output and shove it back through the other way. You should get the original input. If you were to think about chaining these two things together, you put in an x to the function f, this red function f, you get this out, f of x or y, and then if you take that same output and you shove it back through the green function f, that is the inverse of f, you should get back out x, the same thing you started with. So this is the rough idea of what we're talking about. But let's talk about like an actual definition. So let's look here at the definition of an inverse function. An inverse function here. It says, for any injective or one-to-one function, that means one-to-one, that means every input x has exactly one output y. There's no way for you to put in an x and get the same y out for two different x's. Like the x squared function isn't one-to-one. -1 and 1 both give you 1 out. For any injective function y equals f of x, a function, this is read f inverse of x, is an inverse function, this is what we're defining, of f, so f inverse of x is a inverse function of f if f inverse of y equals x. Okay, that's cool. So that's from the picture up above. That's sort of what we said in the picture. But a better definition, in my opinion, and its equivalent, says specifically for f and f inverse to be inverses, we must have that. If you plug f inverse into f, or if you plug f into f inverse, you get x out. So f has an inverse f inverse only if you shove the inverse into the original function, you get out whatever the input was, that is, they cancel. Or if you shove the function itself into its inverse, they cancel. Think of a square root and a restricted squared function. I'll show you what I mean by that in just a second. If you get only the input out, then they are inverses. It has to satisfy both conditions. If you shove in one of them and it works one way, but it doesn't work the other way, then they're still not inverses. And it has to work for all x in the domains of f and f inverse. That is, the two functions are inverses if they cancel one another. In fact, this is what we have always meant when we say cancel. There is an inverse element involved somehow. When we've talked about canceling just numbers when we're adding or subtracting them, it's because you added the additive inverse. When you're talking about canceling numbers multiplicatively, it's because you're multiplying by the multiplicative inverse. This, when you say that functions cancel, you're saying that there's an inverse involved. If you're canceling something, there is an inverse involved somewhere. All right, so let's look at this first example, and it's the easiest of them. It says if f inverse of 4 is 1, what is f of 1? So this is saying if you plug 4 into the inverse and get 1 out, this is saying the exact same thing as if you'd done f to 1 and plugged it into the f function, you would get out 4. That is, f of 1 equals 4, assuming that f has an inverse, f inverse. These two things are saying the exact same thing. So what is f of 1? Well, it's just the input that you plugged in. This takes in an output and gives back an input that would have worked originally because it's an inverse. The regular function takes in an input and gives an output. So this just recycles this around. You can think of it that way. So literally, you just say, I've already said it up there, but f of 1 equals 4. Easy enough. Moving on. This is a little bit harder, but we're just going to use the definition to see if everything works out. So let's do it in a nice blue here. Let's write the definition. We'll write it up here one more time. Remember, it's that f of f inverse of x, remember to write your 1 here, it has to equal x, and it has to be the exact same as just flip these two. F inverse of f of x. They have to be the same. Okay, so we're just going to check this. We're going to check this first part first, and then this part. And I said if f of x is 2x plus 3, and g of x is x minus 3 as a quantity, all divided by 2, tell if g of x is f inverse. That is, I'm just going to check this, except instead of writing f inverses, you could just write g's. It's the exact same thing. We're trying to see if this is the inverse function. So I'm going to plug g into f, and I'm going to plug f into g, and it should, if they are inverses, give me out x both times. It has to give it out both times. So if I do it the first time and it doesn't work, then I don't even have to check it the second time. It has to work for both. So here, we're going to check it. We're going to check it forward. So let's find f of g of x. So remember, f of something looks like 2 times something plus 3. 2 times something plus 3. And what was the something being plugged in? Well, we plugged in g of x. So we plugged in g of x, just like this. And now we just figure this out. So this is 2 times whatever g of x was, plus 3. Well, g of x was just x minus 3 over 2. Okay. There's a 2 out here and a 2 out here, so they just cancel. And we're left with x. We're left with x minus 3 plus 3, which is just x. Okay, so this worked. So now let's just find it the other way. So it worked one way, so now we have to find it the other way. That is, we have to find g of f of x. So, what does g of something look like? Well, g of something looks like something minus 3 over 2. So let's write that. Something minus 3 over 2. Okay, and then what did we plug in? We plugged in f of x. So we plugged in f of x. All right? What was f of x? Well, f of x is just 2x plus 3. So this is just going to be 2x plus 3 minus 3 over 2. We can continue. These parentheses are doing exactly nothing. So plus 3 minus 3 cancels. That is, I added a negative 3. I added an inverse function. They canceled. And then 2 over 2, well, this is actually 2 times 1/2, the multiplicative inverse of 2. And hey, look, it worked that time too. So since it works both times, we can say that g of x is f inverse of x. Because I plugged f into g and g into f, and I got out x both times. You'll notice that these are not, they don't even look close to similar. The actual problems when they work out, but they give you the identity element both times. So that's what I mean by this. You plug one into the other, and then the other into one, and no matter which way you do it, if you get just x out, not 2x, not 3x, not x squared, precisely the identity element x out, you're good to go. All right? So, let's look at another one. So this time, we have, in this example 3 here, we have if h of x is x to the 5th, and g of x is x over 5, tell if g of x equals h inverse of x. So we're going to plug x to the 5th into this, and we're going to plug x over 5 into x to the 5th and see if they work. So we're going to find h of g of x first. Or we could find g of h of x first. It doesn't matter which we plug into which. So h of something looks like something to the 5th power. So I'm going to write this, something to the 5th power. And that something that we're plugging in is g of x. And so we're just going to say, well, what was g of x? Well, g of x is x over 5. So x over 5 to the 5th. Now, think about this really carefully. You can do the math down here if you want to. I'm pretty sure that this is x to the 5th over 3,125. I think that's the right math. Am I ever going to be able to get this to look like x? Am I ever going to be able to get this to look like x, doing any form of mathematics? Remember, I can't add, subtract, multiply, or divide anything by it. I have to just simplify this down to get to just x. Just simplifying. I know that I could multiply and add stuff to make it be x, but all I get to do is just simplify it and it works out. That's not possible, so this doesn't work. I don't even have to check g of h of x. I don't even have to check it at all. Specifically because it doesn't work for one of them, then it cannot work for both. If a mathematical statement does not hold for one statement, one part of the statement, it cannot hold for both because it doesn't hold for one. That's all there is to that one. Let's look at another one. Specifically, let's talk about how to actually find an inverse. So previously, you were given an inverse and said, okay, well, you have fun, justify if these are inverses or not, but now you actually need to find the inverse. So think about what the inverse function does. The normal function takes in an input and plugs it into a formula and gives you an output. The inverse is just going to do the opposite of that. It's going to take in an output and give you back the input. So here's the process for doing this. All right, and it's probably worth actually writing down the process. I'm not going to write down the process, but you should probably write down the process. I'm going to say it. First step, copy the equation. So step 1, copy the equation. That's usually your first step anyway. Okay, so 3x plus 2. Now, instead of f of x, we're just going to write y. This is just a quick little thing. Otherwise, copy everything else. So instead of writing f of x, we write y. All right, that's step 2. Step 3, and this is the crucial step, switch x's and y's. Every y, there should only ever be one, but every y becomes an x, and every x, there may be multiple, needs to become a y. So watch this. X equals 3y plus 2. Now, solve for y. So we're going to take this and we're going to solve for y. And this will always find the inverse if it exists. It's not always possible to solve this, in which case it doesn't have an inverse. And sometimes you need to restrict some domains, which we'll talk about. It has to do with that one-to-one thing. But look, when you switch the x's and y's, we go from the normal function to its inverse. Because switching x's and y's means instead of inputting an input, x, now we're inputting an output. So obviously whatever we find is going to be the opposite, or the inverse, of what we're doing. So let's solve this real quick. So we subtract 2, and we get that x minus 2 equals 3y. And then we divide both sides by 3, or multiply each side by 1/3. And we get that y, I'm going to flip this around, is x minus 2 over 3. And then the last step is, once you've solved for y, instead of writing y, write f inverse. F inverse of x is x minus 2 over 3. That's it. This is its inverse function. If you want to do something fun and extra, and my definition of fun, but if you want to try to see some patterns, if you want to try to go beyond the mathematics of what I'm showing you here, go graph both of these on Desmos. I challenge you to do that. Pause the video and go graph both of these. When you graph them, by the way, just call this g of x. Don't try to do this garbage. Just call this g of x. Graph both of these and see if you notice anything. Specifically, when you do that, also graph just the identity line, y equals x, this special thing that we're needing, and see if you can tell anything about it. If you want to, go back in the video and do the exact same thing with the previous one that actually worked out. Graph both of those as f and g, and also graph this extra bit here, and see if you can notice a pattern, because that might be a problem on your test. Regardless, let's look at another one. So here we're asked to find the inverse of f of x equals the square root of 3x plus 1. So we are skirting the definition of what we need to do. So check to see if this is 1-to-1 first. If it isn't 1-to-1, it isn't going to work. It was 1-to-1 the previous 2 times, because it was either an odd function for x to the 5th or x over 5, or it was just a linear function, just a straight up line. And we know that that's 1-to-1 because it's a line. This is the square root function, and this is in fact 1-to-1. We know that. Just the principal square root, just the positive part, not plus or minus. That would not be 1-to-1. That wouldn't even be a function, in fact. That would be 2 discrete functions stitched together, but I digress. So it's going to work on this one. A little note, about x squared here in a second that I'll talk about, but let's find the inverse of this first. This is a little bit harder, but we do the exact same thing. So we write it again. F of x equals the square root of 3x plus 1. Okay. So we change our f of x to a y, and we write 3x plus 1 under the square root. And then we switch x's and y's. The square root of 3y plus 1. Now, all we have to do is take this and solve it. So in order to solve this, if there were anything out here in where our d is or where our a is in the general form, we need to get rid of that first. We'd get rid of the d first, then the a, then we get rid of the square root. You get rid of a square root by doing its inverse operation. That is, we square both sides. When we square x, we get x squared. When we square a square root, we get what's underneath it. Okay? That is literally what I did, and I'll do it up here in red. But what I did to both sides of this was just square it. The square of a square root cancels. Why? Why is that true? Remember that the square root of x is just x to the 1/2. So of course that means that the square root of x squared is just x to the 1/2 all squared. And of course when you raise a power to a power, you just multiply the powers. 2 times 1/2 is 1, and x to the first power is just whatever was underneath it, x. That's it. So this just equals x. That is, the square root of x and x squared are inverse functions. So we just actually verified that. We did it one way. We'd have to do it the other way to actually verify it. But this is what's going on. The square root of a number is just that number to the 1/2. Anyway, we're just going to finish solving this for y. It's easy enough. We subtract 1 and divide by 3. And we get that y must be x squared minus 1 all divided by 3. So then our inverse, f inverse of x, is just x squared minus 1 over 3. So that's it. So that's all that there is to finding this. Now, please be careful, because if you were asked to find the inverse of this, if I just said straight up said find the inverse of f of x equals x squared minus 1 over 3, you are going to get this. This is its inverse. Obviously, if you go the other way, the inverse of f inverse is f of x. Obviously. However, be very careful, because x squared minus 1 over 3, but x squared in particular, is not 1-to-1. X squared minus 1 over 3 is going to look something like this. Okay? This is actually 1/3 times all of this. So if you distributed the 1/3, this is 1/3 x squared minus 1/3. So this is going to be a parabola down here at minus 1/3 with its vertex. And I'll draw it in red. And it has been vertically compressed by a factor of 3. That is, there's a 1/3 in front of the x squared part. So it's going to look a little more wide open. And I'm not trying to get it exactly correct, but this is roughly what it looks like. And by the way, if you can't do that off the top of your head, go back and do some more practice on 1.5. You need it. But this is roughly what it looks like. Notice, please, this is not 1-to-1. I can get, for example, whatever these zeros are. By plugging in 2 different values, I get out the same y value. If I can plug in a value over here and get the same height here as I get for plugging in a separate value over here. And since this is symmetric, if I plug in positive 5, I'm going to get the same answer as plugging in negative 5, because this square does away with that extra information. So what we have to do with this is restrict the domain. That is, we have to say, you know what, I only want this half. And this is going to be called the principal part of the domain. Just a little bit of extra knowledge. So what you say is, when you do this, before you start doing it, you just say that for x greater than or equal to 0. Or if you want to be super mega fancy, you say x in the domain from 0 to infinity, if you want to use interval notation to do it. Let me write that infinity a little bit better so it doesn't look like absolute trash. There we go. So this is the kind of information that we're talking about. So this is the restriction that you'd have to put on the domain, so that you're only talking about this right part of it. At which point, if you're only using the part in quadrants 1 and 4 here, obviously that's going to work, which is why you're going to get something that looks kind of like this. Here, let me do it in green. Let me do it in the original. Well, yeah, let me do it in green here. You're going to get something that looks a little bit like this, roughly, when you do the... It's going to arc, though. It's going to look a little bit nicer than that. But you're going to get that square root. And by the way, go graph this guy with this domain restriction, or only consider this part, and then also graph this, and then also graph y equals the square root, y equals x rather. And you'll notice that it just reflects this over that diagonal line is all that it does. That should be the thing that you're noticing. But seriously, go look it up so that you know what's going on. All right? Let's look at another thing. The last thing, in fact. And this is one where you have to be careful with the domain, and you're not always told this, but you have to find the inverse of this. So you'll notice that this is a square function that has been vertically stretched by a factor of 2. It's been moved 3 units to the left because this whole thing is positive, and it's been moved 1 unit down. We want to find the inverse, but it's not 1-to-1. So what do we need to do? We need to restrict the domain. So first off, it helps to think about where this thing's drawn. So let's think about where this thing's drawn and where we need to cut it at in specific. So let's think about this. We've moved it down 1 unit and to the left 3 units. So it's about right here. Okay. So this is about 3, -3. And this is about -1. And then it's also been stretched vertically by a factor of 2. And it does not quite matter what it looks like in terms of the stretching, in terms of restricting the domain. What we need to restrict it to is the most positive part of it, which is the part to the right. So we need to restrict the domain to be everything greater than or equal to -3. That is, we want our domain of our function, because this isn't 1-to-1. Right now, plugging in a number over here jumps up to this point. We can get to the exact same point by plugging in a number over on the right. That is, let me actually show you here. Taking, for example, this point here would give me this point here. I can get the exact same point by just plugging in whatever this is over here. And I don't know what it is, but notice how 2 different inputs gives the same level of output. That's no bueno. So we only need 1/2 of it. Now we could choose the negative part, the more negative part if we wanted to, but that's not tradition, so let's not do it. Instead, let's say that the domain of f, okay, is going to be equal to everything from -3 onward, and we can include -3. Now, maybe you don't want to draw this in order to get this information, so how do you know? All you do is you take the input of the function, literally everything inside of here, everything that I've underlined, x plus 3 in this case. All right? You want this to be greater than or equal to 0. So you come over here and you do x plus 3, just what's inside. That's it. Greater than or equal to 0, and you solve it. Well, it's x greater than or equal to -3. And then you write it in interval notation, and you get that. That's it. That's all you do. You want your input to be greater than or equal to 0, and that'll give you everything else that you need. We do not care if we've moved it over. We don't care how we've stretched it. We do care how we've compressed it, though. But other than that, you just solve this real quick, and you're good to go. So, once you've done that, once we've restricted this, now we can actually find f inverse. So after we've done this, after we've made sure that this is going to work out, now we can find f inverse. So here's f inverse. We write the function again. F of x equals 2 times x plus 3 squared minus 1. Okay, look here. Semicolon. Okay, for x greater than or equal to -3. This is what you write before you can find it. You can't actually find the inverse of this. It's not 1-to-1. You can't do it. But you can modify the problem a little bit yourself so that it's doable. Do that for me. Now that it's done, you just blindly follow the math. This is one of those situations where blindly following the math, that is doing the process, calling this y, x plus 3 squared minus 1. You don't have to write this each time. Once you've written it once, you're fine. Switching the x and the y. Minus 1, right? And then going through it. You can do this without actually doing any of the domain restrictions. Obviously, you can get away with that. However, it's not going to be correct. You will have, if you don't do this domain restriction, you will have actually found the inverse of a function that you can't find the inverse of, and it's just not correct. So go ahead and solve this. It isn't hard. Get rid of the d, get rid of the a, get rid of the function, get rid of the c, then get rid of the b. It's always in that order, by the way. If it's given to you in general form, it's super easy. Barely an inconvenience. So let's add 1 and divide by 2. So x plus 1 over 2 equals y plus 3 squared. Okay. Now we're going to take the square root of each side to get rid of this square, just the positive square root, because we're only dealing with positive, the most positive part here. So we take the positive square root of both sides, so we get positive square root of x plus 1 over 2 equals, and then on this side we just get y plus 3. Okay, and then we're going to end with, and we'll do it right here. All right, here's the final product. I'm going to put the y over here, and then we just subtract 3 from both sides. On the outside, x plus 1 over 2 minus 3. So finally, we can end with f inverse of x equals that. X plus 1 over 2 minus 3. And that's it. Specifically this. Okay? And that's everything. That's everything that you need to know.